Hello, hello. Mhm. Really? Ah, I know why. Let's see. Hmm. Nope, that one. Well, that's kind of weak. Oh, catch. There we go. No, I didn't turn it off. I finally fixed my headset. So I dropped my cable. Don't need it anymore. So basically, I bought this pair of cans here to, well, mainly for listening to music, and then it's turned into my teaching headset, but I bought it because they're Bluetooth. And for the longest time, I couldn't get it to actually pair with my laptop. Something to do with the Bluetooth device. Finally figured it out. But, ha, get rid of that. But 3080 Ti. Sounds nifty. You kids with your desktops. Can actually do stuff with it. I think the last desktop I owned was probably in 2002. Intentionally owned. I've gotten them through school, but yeah. All right, we have audio. So you all are fortunate in that my morning class we were having network problems. So we had a whole 5 minutes of me trying to figure out what was wrong with my network. It's lots of fun. Hmm. Video cards. Fun discussion. And then after you buy it, it will either go on sale or the next version will come out, and then you'll feel bad. I assume that will last you for a while. Anyway, let's talk class stuff, since we only have an hour. So, sorry about that. I got my book stash over here, and I noticed my kids were rooting through them. So we have 2 weeks left of class. Yay! That means we got this week, we've got next week, and then the week after, Monday, is finals. So you are almost done with me. Woo! Unless you stick around for computer graphics, which is also going to be fun. But the plan is, if you remember, so Monday is the 14th, so December 14th is when our exam is. It's all part of the game. Um, so we're going to do final presentations for your projects on the final exam slot. So it'll be just like we did for the midterm. We'll do either a Blackboard or a Zoom session. Haven't figured out yet which one I prefer because I know Zoom added a bunch of features which I complained about before, them missing. So we'll get that up and running. So this week, Monday and Wednesday, so today and Wednesday, we're going to do normal class. Friday, we will be doing a group session, so it'll be on probably Zoom just to try it out. Basically, now that we're kind of in the end game here, I like to give you some class time to work on your group projects together. And it's not going to be like a required lab or anything like that, but basically I'll split everybody off into breakout rooms and I'll kind of pop in and out of people's discussions and basically just want you to work on finalizing things. And your next assignment, which actually if I could get somebody to remind me when 140 rolls around, I'd like to talk about your final deliverables, because basically you have one more thing left to do, and that is your final documentation for your project. Now, I know you have a lab due Friday. You got 2 weeks to do something that probably shouldn't take you more than an hour tops to really get done if you have problems. But I'll get you the requirements for all the final documentation within the next couple days. Just kind of fine-tuning some of the gotchas on there. But basically, you're going to be doing updating your requirements, adding some test cases, the lab with IntelliJ. Yes, so thanks for reminding me. I sent out a follow-up announcement about IntelliJ. If you were struggling, check the announcement. I have a separate little manual that I made for IntelliJ. If you use Gradle, I didn't try with Maven. Yeah, Eclipse is fine too. But the Gradle in IntelliJ took me probably 10 minutes, and I have no idea how to use IntelliJ. So I would check that out if you're sticking with IntelliJ. But honestly, it wasn't that bad. It was actually, honestly, it was easier in IntelliJ than it was with Eclipse. So I will say that. But if you are struggling with it already, that probably sounds counterintuitive. But yeah, check that if you're having issues. You have until Friday again to get that done, don't worry. But yeah, so we've got that. And I'll send out an announcement for Friday just so that we're all clear on what's going on. But yeah, last 10 minutes of class, we'll talk about what we've got coming up due. So without further ado, we should start talking about verification and validation to start wrapping things up here. So I know we've kind of been talking about testing in a very high level, right? We looked at unit testing, did some fun examples, kind of described integration testing a little bit. But now we really have to kind of get into what verification and validation actually is and how it is basically a necessity for any good software engineering project. So we're talking about dynamic and static verification today. Probably gonna end about psychology-ish for software testing. But basically, I want you all to have kind of a good firm ground for what you need to be doing with your projects. And again, the hint is going to be, well, you're not going to be the one doing the testing, right? It'll be the people in the quality assurance department. But we'll get to that. Anyway, I came across some lovely quotes on the internet. I've got them popping in very slowly to give it the effect that it needs. But here's some fun ones. All code is guilty until proven innocent. I love this one because it has that very cynical and jaded view of software that I have. So, great quote there. Fast, good, and cheap. Pick any two. There's your triangle that you may know from the Agile realm, right? You get two out of the three based on what you put into it. You know, software that's fast, software that's cheap, but it's probably not going to be good because you put all your effort into making it fast and cheaply. So, kind of a nice point there. Quality is never an accident. It is always the result of intelligent effort. Key takeaway here is that the amount of effort that you put into your quality assurance, the better of a product you will have. It's not just going to happen accidentally. Then, it's more about good enough than it is about right or wrong. So the trap that we're going to fall into with testing is wanting to spend all of our time making sure that it is perfect, that we have zero bugs, that it is performant and optimized, that everything is just amazingly beautiful. That is never going to happen. Your software has to be good enough, and you have to be willing to release it into the world. Now, with that, it shouldn't be like crappily tested, right? You should actually put the effort into making sure you have a good product and that it's not going to have a lot of failures out there. But there is too much testing you can do, and then you can basically get into this downward spiral of always testing, always testing, always testing. Basically, you want to make sure it meets your requirements. You want to make sure your customer's happy with it, that you don't have any significant flaws, and if it is good enough, meaning that you don't really detect any showstoppers, it's time to let it go. But good enough is something that we'll kind of keep coming back to. Nice little quotes to set the stage here, I think. Now let's actually talk about V and V. So this is the V and V that you probably have heard of. I've mentioned it many times in class so far. Basically, these are the quality assurance aspects of taking this big software project, making sure that it is A, of a good quality, and B, ready to be delivered to your customer. So what are verification and validation? I know we've kind of used these quotes before. Verification means that what we're building conforms to its specs, and these could be requirements, they could be models. Basically, you are checking internally to make sure that what you're building is right, effectively. Validation is going to be the other side. What you have done, does it meet what the customer is expecting, right? Does it meet their acceptance criteria? Another way you can kind of think about verification and validation, verification is more of a rigorous, formalized procedure. Maybe it's doing logical models. Maybe it is doing walkthroughs internally with your team, going through your specs, going through your use cases, making sure everything's correct. Validation's more taking your product and testing it in the real world, right? Does it actually do what you're saying it does in these real world conditions? Now, there's multiple ways to come across V and V. If you're from a more of a software research kind of an area, verification is going to be model checking. It's going to be digital logic. It's going to be all kinds of mathematical proofs. Validation is going to be your testing in all kinds of different environments. Basically, there's different ways to look at it. For our perspective, we mainly care about our specs and what perspective we have. Is it internal or is it customer focused? We can do testing and verification. We can do model checking and validation. It kind of goes both ways there. Key takeaway. If we do a lovely job in our V and V procedure, audio cut out again. Really? Can we hear me? So I'm seeing it looks all right from my perspective. Okay. Sorry, we were having issues in the morning class, so I was concerned that it happened again. All right. So the one key takeaway here, let's say that you have done months of testing, months of verification, and you think it is ready. Now the question is, are there any bugs left? Probably. The purpose of testing, verifying and validating, is to detect all of the common bugs, all of the things that are going to be trapped by what you have specified in requirements. You are never going to catch every single bug that exists in your program. And again, there was a bug that cropped up in Hello World after years and years and years in a C program. So with I think the puts command had an issue with it. Basically, you just need to make sure that your software is being built to your specs. Yeah, so let me pop all these up here. So if we look at it from the verification side of things again, consider this more your internal specs. You have dynamic and you have static analysis or verification basically. Dynamic is going to be basically your testing, right? So think of the term dynamic versus static again. Dynamic things are changing, static set in stone. Dynamic means you're actually testing your product against something, right? You're running your program, you're giving it inputs, and you're seeing what the outputs are. We're dynamically testing it. Could be a prototype, could be an executable version, meaning like your built application. Basically, it is something that can run. And what did we look at with our test cases before? What are the inputs? What are the steps for running the test? What are the expected outputs? And what did you actually see? Right? So if you have outputs that match, it passes, right? It means that it does what you expect. If it fails because your actual results don't match what you expect, that's a test case failure and you have a problem. What's the problem? Well, you have to go and debug and figure it out. This notion of actual versus expected, also called a software oracle, meaning that it tells you if this test case passes or fails. It's basically your acceptance criteria for the test. But that's your dynamic. We've been talking about this. Now, the static verification, which we've kind of alluded to, but we haven't really gone into great detail on, this is where you walk through all of your artifacts. So your requirements, your UML models, your design documents, your source code, all of your various artifacts. You go through and you formally check them. And that could mean walking through requirement by requirement. Is this worded correctly? Is this clear and unambiguous? Kind of like what I gave you for feedback for your software requirements. Does it make sense? Is it implementable? Does this use an anti-pattern? Is there some notion of failure that could be brought in at some point here? Basically, look through all of your artifacts and make sure it works, including your implementation. And with static verification, you can apply it at any point in the process too, from very early on to delivery, basically. Now, you may have heard of static analysis in other ways too, so there's a lot of automated static analysis tools. Some of you may or may not have used a lint. And I realize I'm kind of clipping here. Let me dial my volume back a little bit. This is basically a static analysis tool which checks like variable types, checks the coding standards that you may have. Basically, it goes through and statically analyzes your program to make sure everything is as it should be. This is done pre-compiler, basically. Checks maybe some of the gotchas. So for instance, there, if you have let's say you have a coding standard that you follow in your company, and I still have yet to read the Grand Valley coding standard. Like the one that we used to have, if you had an if statement, you needed an else statement as well, regardless if it had anything in it or not. So if value is greater than 10, print out output, else do nothing. That was for a safety critical bit of software that you have to account for every single path of code. And that was part of our static analysis check, basically. So there's lots of automated tools for that. It doesn't just have to be for C. It could be for JavaScript. It could be for Go, Ruby. I mean, they're all available for pretty much any language. Probably emoji code too. Wouldn't be surprised. Realizing my face is cutting off this here. Oops, let's not do that. Just says results. Let's go back to the bottom. So one of the other ways you can think of static analysis, and let's consider it from a coding perspective. Basically, you're taking your program and you're breaking it down into pieces. Basically, you're transforming it into something that an automated tool can read. So let's say you have some source code here, right? It's your int main, do a bunch of stuff, then return. What you can do from that is extract all the symbols, extract a model out of this, extract the control flow graph, which basically shows you how you go from point to point to point in the code, right? Is there a branching statement? Is there a loop? Is there a function call? Yeah, Pylint. So it's a pretty common analysis tool. But the key here, these are all different representations that you can get from static analysis. And these tend to be handy for automated tools. What can you get out of this? let's say I look in my control flow graph here, and it's kind of hard to see, obviously, but we see like a little loop happening here. We see a big loop happening here. See a branching statement, and you have basically a graph problem, right? What you can do is you can identify, are there any dead code branches? Is there maybe a path of execution that never gets triggered, regardless of the input or output? Is there a accidental forever loop or infinite recursion? These are all kinds of things you can detect just by looking at your code in a different representation. Or look at your symbols table here. If you have a variable that you're storing string data, yet you've defined it as an integer, the compiler is not going to like that, or it may try to automatically help you out. It depends on the language. But a static analysis tool will tell you, hey, idiot, you used the wrong variable type. Fix it. So that's kind of one of the other things that you can do here when you're analyzing code. Again, this is more automated. These are also things that you can walk through in, say, a code review with your team. Most of them are. It depends on the tool. Some of them are paid, some of them are licensed, some of them are open source. If we look at lint static analysis, where is the actual tool? Like lint for C, C++, you can just download and install, basically. We had a plugin for Visual Studio that we used, but I mean, there's paid programs out there too. But yeah, they all have to be configured generally as well with what you want them to do. But they are very handy for, say, auditing purposes too, right? If you are in a company where your code has to be audited by somebody else, meaning they come in, they look at all of your, say, static analysis reports, your test reports, are you doing what you say you're doing? Do you have X% coverage of all your statements? And they're going to look at these reports and say, you screwed up here. You are not properly checking this branch of code or something of that nature. These are basically all things to expect as you work, as you get out into the working world, that it's not just writing code, it's all of the extra quality assurance that goes with that. So now that should make sense, right? We're testing and making sure our software says what we say it's doing. Can we take this verification activity, and apply it for validation, right? So can we take what we're doing internally, give it to the customers, or vice versa? And the answer is absolutely. If you think of verification as more of a formal, rigorous procedure, why can't we bring in that real world data that the customer would have to make sure that it meets their standards, right? You can get an even richer set of testing done, kind of by merging these two. Now, the other thing to consider as well, if we think of verification as a more formal, rigorous, like a model checking kind of activity, and when I say model checking, I should probably define that. Basically, if you have a model, say, like a control flow graph here, your model would basically say, look and say, is every single path accounted for? Is there any set of conditions which would cause you to go into a unexpected state, or do you break your program by applying this, this, and this? And it's a very formal, rigorous mathematical proof that gets applied behind the scenes. Could run very quickly, could take days to run, just like some of our test cases. But if we have this simulated internal idea of what the real world looks like, bringing in that rich environmental data set can augment our activities. So V&V, very, very important aspect of the development process. Now here's a quote from the Art of Software Testing, and I love this quote. Testing is the process of executing a program with the intent of finding errors. So basically, you are trying to break a program when you do testing, right? You don't want people to blow smoke up your behind and say you have the best program in the world, you pass all your test cases, but those tests are useless and showed you nothing, right? You want your program to break so that you can fix it, so that you can harden it against the real world, right? So testing is something that is very necessary to have. So what is a successful test? You tend to why am I stuttering all of a sudden? You tend to think of a test as something that you want that check mark, right? If all your tests pass, you can move on to the next step. But think of it the other way around. Testing tells you what you did wrong. And it doesn't have to be that you screwed it up. It could be that you did something unintentionally. Maybe you missed a use case. Maybe you missed some kind of a user type that you would never expect to be able to have to handle. Basically, it's going to tell you if an error exists and what that error is. Does it catch all of your errors? No, that's mathematically impossible to generate a catch every single flaw, but testing will help get you there, gets you to that good enough state. So we're going to detect the presence of errors. Now let's say that we build up a test suite. And what is a test suite? It's just a sequence of test cases that we execute, right? We can have multiple test suites. Run all of my test cases that deal with movement of my character. Run all my test cases that check to make sure that my magic mirror can go out and talk to all these various APIs. Does it render to the screen correctly? That would be a different test suite. If they're all passing, right, every single test suite that you have still doesn't mean that your program is perfect. It just means that we never caught that particular glitch. The way you kind of have to realign your brain for testing is that no test suite or testing strategy is ever going to be fully complete. There's always going to be something that you don't detect. You just have to try and catch as much of it as possible. And with that, you really have to catch all the glaring safety related ones, right? Because you don't want to release something that's actually unsafe. And kind of the other key here too is that there are a lot of people that have been working on testing for a very long time, and we are still not at that perfect testing strategy, right? There are so many deviations from the standard testing strategies that are out there to try and reduce testing time at the cost of not doing enough, maybe do really weird things at the bytecode level, and there's all kinds of really neat stuff you can do, but we're still not perfect. So let's talk about psychology a little bit, because this is kind of an interesting way to think of things. So with testing, you have to be in the right mindset. And generally that means that you, the developer, are not the right person to be doing the testing. We've done this over and over again. Don't test your own code. Don't test your own code. And it's actually a psychological thing because when you are writing code, you are building something beautiful and wondrous, and it's this amazing creation that you're going to inflict on the world. And if you're testing, your goal is to break it, and you want to utterly destroy this program. Right? And I'm not mincing words at all here. You want to break the F out of that program so that you can demonstrate what all of the other people who are going to come out now and use your program may do to it. You, the programmer, never even thought people would use it differently. So your goal is to break things, and you want to break them as much as possible. So let's make our programs behave incorrectly. Let's cause them to segfault. Let's cause them to do really wonky things. And we're going to show our designers, or the programmers, what they have to do to fix it. So psychologically, and where we're coming back here, you, the programmer, don't want to destroy your creation, right? You want to demonstrate in the best possible light what you've created, and that's human nature. Now, you think you might be able to take that, you know, I own this program, it's lovely, it's mine, it's wonderful. You want to divorce yourself from that notion, and I'm going to be the tester. That's fine. You might get half of the bugs that are out there, but there's always going to be some piece of you that doesn't go down a particular path of testing. You might claim it is too much effort or too much time, or that's never going to happen, but there's still always things that will crop up. So just something to be aware of. It's a very hard mindset to do. It's almost like, if you were to write a book or something and you think that you can edit the book by yourself. No, that's why there's all these professional editors out there who do that for you. They tear it to shreds. So don't test your own program, basically. The fun part though. We spent all of last lecture talking about how you should do test-driven development, how you should write unit tests by yourself as part of making your programs. So I'm going to pop this question into the chat here. How does not testing code yourself? Excuse me. I am very intentionally asking you this question, and these are two completely different viewpoints. I am telling you, do not test your own code. I am also telling you, test-driven development is actually not that bad of an idea. You should maybe try it. How can I tell you both of those things at once and not have some kind of a matter-antimatter explosion happening here? How does this dichotomy actually work here? Because that's the only emoji name I can remember. Unit testing is different from testing once the product has come together. Yep, that is definitely one argument there. hmm Different perspective, right? So if we are unit testing, we're just checking the inputs and outputs of a function or a class or something like that, right? Some little atomic object. It is still possible to overlook things at that level, though. TDD doesn't imply you're the only person testing. Ah, that's another good point. Right, you might not be the only person writing those test cases. But when we talked about TDD, we said you should write the test case before you write any code, right? So another perspective here is that if we are doing the TDD approach, we haven't written any code yet, so we have nothing to avoid, right? We are writing our use TDD during making, use other for final test. Yeah, so there's levels of testing, right? There's integration testing, there's system testing, acceptance testing, all kinds of different layers, and those are all definitely done generally by different people. But with TDD, you're not necessarily breaking your own program, right? You're writing tests that check your requirements that you have. I have a function in my class that needs to convert from Celsius to Fahrenheit, right? I have not written a line of code yet, but I can write a unit test that will check that. So I'm not really destroying anything at this point. Plus, I'm building up my test case library. If you're coming into TDD late, though, you've written all your code and I'm going to write out my unit tests, then you might have a problem. Then you need other people. So yeah, just something to consider. The back and forth there is definitely a real thing. Okay, so why do we have different kinds of testing? Might be your next question. And I'd say, that's a great question, all of you. So the first thing you might think of with testing is let's do brute force exhaustive testing. Let's test every single possible configuration of our program. And both of these images you can very easily find on Google Images when you search exhaustive testing. So this is from an exhaustive testing book, I believe, and this one is, hey, we've passed this test case, now we're at test case 5.5 million. What is exhaustive testing? Testing, again, every single possible value that a variable will take. Now you can do this in black box and white box format, and I said get used to black box and white box, it's going to come back to haunt you. Here we have it again. Again, black box is you only know the inputs and what the outputs are. White box, you know what is inside, so you can test out your algorithms, test out the paths of execution, expressed behaviors, that kind of a thing. But exhaustive for both of these means let's check everything. And hey, is this feasible? Is this something that we can reliably do? That might be a good question for all of you. Is exhaustive testing something that is feasible? Let's say I have a Java class where I'm doing that simple calculator from our Travis lab, right? We can add, subtract, multiply, divide. And I want to exhaustively test those 4 functions. Is that feasible? Honestly, it's a simple program, right? There's nothing too crazy there. What do you all think? So let's say we have, if there's a finite number of inputs, it's possible. That is the key. Thank you. Finite. Finite inputs is possible. You still get into this weird combinatorial realm of how many test cases you need, right? So again, consider testing being writing a test case for every execution. So if I'm testing 5 plus 5, it should equal 10, right? So that's one test case. What about 5 plus 6, 5 plus 7, 5 plus 8, 5 plus 9? So that'd be, each one of those would be a separate test case technically. So it's really not feasible. Generally, it's mathematically impossible, honestly. Um, Now, to your point, if you have a finite set that you're testing, right? Like you're testing an enum or a range or something very, very non-exponential in terms of how many cases you'd write, sure, that'd be possible, but not for all programs. So with that, we need systematic testing techniques, and I'll give you an example on the next slide here. But systematic testing basically means let's focus on one particular thing and try it out. One of the testing types we'll talk about next time would be um, like branch coverage for one, or boundary conditions. Basically, instead of testing every single input and output, you check something within the range that you're expecting. You check something just outside of that range. So for instance, if I'm doing a unsigned integer addition, so it's like 0 to 2 to the 32, the possible integers, I would check 0, I would check somewhere in range, I'd check at the max, and then I'd do the max plus 1, or the minimum minus 1, or something like that. And that's all the testing I would need to do there, right? We're checking the boundary, the edge cases. We assume that what is inside is a representative value, right? Because if I do 5 plus 5, or I do 5 plus 100, I'm not going to have any weird interactions happening, right? This set of values is representative. But if I go outside that and I throw like a -1, what's going to happen to my program, right? If it is an unsigned integer, it's either going to cast it to 0 or it's going to break apart and you get a big test case failure, right? So systematic is basically let's reduce the amount of test cases that we have to run, but still get a good testing strategy to happen. So here's a good example, and it's actually integer addition. So here we have how long is it going to take to actually test this program. It is a simple function. It's a summation, a plus b, and that's all you're doing. Well, if we are brute force exhaustively testing this, that means every possible value, every possible combination, that is 2 to the 32 times 2 to the 32, which gets you 10 to the 19 test cases that you have to run. All right, and this is, again, kind of an overstated, simplified example, but that's what exhaustive testing means. You don't leave anything out. You test everything. Again, to your point, something like a set or a range or an enum would be a lot better here. You wouldn't exhaustively test something like this. But if if we were to run this sequentially, it would take 600 years for every nanosecond test that gets executed. So this will take time and it will take processor power. Now you could say, well, yeah, that's silly. Just parallelize it. Yeah, it's still going to take a lot of time to do that, right? Because you need the resources just to test this. And look at how stupid simple this program is, right? A plus B. That's all you're doing. 80 years. Do you actually do the math? Um, this is a non-complicated program, right? Start adding in other things. Maybe we also have to start instantiating a drawing surface, read in tile map information, do all kinds of calculations for vector-based location and direction and all that. Goes from 600 years or 80 years to, even more. So the key takeaway is basically that we really want to get as good of a testing strategy that we can have within a reasonable amount of time. And that's honestly, it's often why testing is done in parallel to development because it does take a lot of time. So, with that, we have good strategies for that. Your kind of key takeaway for today is that when we do testing, we want to find the largest amount of errors that we can find in the least amount of time with the least amount of effort. Okay, you don't want to be sitting there exhaustively testing a program. You want to check to make sure that it's going to do what you say it does and leave it at that, basically. Now, if you get into a safety critical kind of thing, that's a whole nother can of worms, but basically we have a lot of effort to do here. So let me pop over to the end. End, please. Nope. Since we are just about at 150 and I want to talk deliverables, just present, thank you. So, testing, very important strategy. Again, you should all be comfortable testing by the time we're done here. And I've kind of been dropping little hints along the way that you're going to have to be doing testing for your term project, right? I think I said at the beginning of class, it's something to keep in the back of your mind as we go. So, what am I asking you to do? Well, and keep in mind, these numbers are slightly approximate. Don't take this for the gold standard. Look at the document that I'll be providing you shortly. But just to give you a feel, I'll be expecting some unit tests. I'll be expecting some integration tests, and I'll be expecting some system tests on your final deliverable. Now, what are these things? Again, a unit test is the smallest level of functionality you have. It could be a function, it could be a class, it could be checking an API call, basically some little thing. And then you're going to say, well, Professor Fredericks, I'm not using Java or Python or emoji code. And I'll say, ha, I got you. You can test manually too. You don't have to use JUnit. You don't have to use Python's unit test or nose or anything like that. You can just write a little test case and manually check it. If I hit the left arrow, does my character move? If I plug in the power to my magic mirror, do I get data from an API? Yes or no? It could be something that you literally just manually write as a test case, and then you say, yep, it passed, or no, it failed. And then you figure out why did it fail. So unit test, small piece of functionality that you have there. Integration test, take what you've done, take another module, integrate them together. Does it still work? Does it pass whatever test will show you if this code works together or not? Yes or no? Again, it doesn't have to be automated. It can be manually run. And then system test, something you do at the very end. Does your whole system work together or not? Right? Do you have a entire, let's say go back to the you're making a game example. Oh, okay. At a delivery. You're making a video game, right? If you have a player and an NPC and an enemy on the screen at the same time, can you walk over and talk to the NPC? Can you walk over and attack the enemy? Can you pick up the widget that makes you win the game? Whatever it is. But the system as a whole. Basically, what I'm trying to get you to think of is writing test cases at different levels of abstraction here. And again, if you're doing something in RPG Maker, you don't have to do an automated testing strategy. It can literally be just, here's my test case, here's the inputs, here's the outputs, does it pass or not? Yes or no? And these are approximate numbers. I don't want to overwhelm you with testing this late in the semester, so I may tweak these slightly. Either more or less, kind of depends how I'm feeling, I suppose. And, if you're freaking out when I announce this here, I will be giving you a template to fill out, so it's not going to be just come up with them on your own. I'll give you fields to fill out and to basically mark up and things of that nature. Other point, your next assignment, which I'm kind of alluding to here, will be your last one. Ooh. Basically, this is your final documentation that you have due. So with that, I know I got some questions last week on what are the deliverables going to be. I'll put that up in the next day or so. Did I just start duplicating my voice? I swear, Bluetooth is not the best here. Weird. I'm getting like duplicated sound in my ear. Fun. Love technology. So your last assignment's going to be your final deliverables, and all I'm really going to be asking you to do is to revise your requirement spec based on the feedback I already gave you. Add in some testing, clean up your diagrams, link everything together. So remember we talked about traceability a while back. Does test case 1 impact requirement 1 or NFR 1? Or does it talk to UML diagram 5, for instance? So how does your system all kind of hook together? Right, and all these artifacts you've been working on, you can very easily, you know, link things up, I would say. So as a reminder, Monday, if you came in a little bit late, the Monday of finals week is our final exam slot. That'll be your presentation time. The deliverables I'm not looking for until Friday of exam week. So basically, you've got the entire week to formalize and finalize everything that you need to do. And the reason why I kind of set it up this way is I know you're all going to be probably freaking out about your exams, and I don't want you to have a massive push to get this done when you could be studying for somebody's final. So if you need the week for finals to get things turned in, that's fine by me. Basically, the deadline is the 18th for all of your documentation. If you get it done sooner, feel free to turn it in sooner and I'll grade it sooner and then I'll put your grade up for you for that. But if you need the extra time, basically I'm building in a little buffer for you. And again, this Friday, this week, we'll be doing an in-class kind of collaboration thing. It'll basically be time for you all to work in your groups, and I'll pop into each breakout room and kind of see how you're going and guide you along and things of that nature. All right, so yeah, basically the key with these sessions too, if we were in class, I'd say this is going to be an open session where I'm just going to wander around and talk to everybody and see how everybody's doing. Maybe help guide you or help scope things, but use it to your advantage. Don't take it as a wasted hour to go sleep. Actually, make it worth your time. Otherwise, it's not helpful to you. But any questions at all for the homework types of stuff that's coming up? Or is it fairly clear? Obviously, you'll be waiting for the actual spec that I'm looking for, but hopefully at least the idea makes sense. We got our GIF there, but alles klar? I think it's mostly clear. Yeah, so let me let me do this maybe. I'd give you something kind of like this, and this is not going to be what it looks like, but it'll be something of this nature. So what's the test case name? Test case ID, test case description. So you'd basically just fill out the right side of this. So what is the name? What's its ID? What is it? Inputs, expected outputs, output. I'm gonna need some more. There we go. Actual output. And then you'd also have traceability. Jesus, there we go. So you'd almost, this might not be actually how it looks like, but it would look something like this. Basically, you just copy and paste this table for every test case that you have. So if this is a unit test, you'd have something like unit test, or no, it'd be, let's test edition 1. unit test for add numbers function. Something of that nature. Inputs. Yeah. It's 1 plus 0, 1. Actual output, -5. Fail. I'm just completely making stuff up here. But this would basically be what I'd be looking for, something of this nature, right? And hopefully you can kind of see how this is something you could do by hand. You don't have to write an automated test. And if you want to, that's fine. I mean, if you want to unit test the heck out of your program, go right ahead. Then you can just easily generate this table, right? You don't have to go through and do this manually. Um, but this is something that kind of extends to any project, not just a straight up, JUnit or something like that. But yeah, nothing too crazy. It's gonna look like a lot of paperwork, but honestly, it's really not all that much. Do you have to write what type of, yeah, so you're gonna have to do specific ones as well. You have to do unit test, system test, integration test. So if this was an integration test, the table would be the same, so that's probably a good point then. So let's do test type. I swear I know how to type unit. So this could be unit or integration or system. So pick your current version, basically. But yeah, that'd basically be what I'd be looking for. And again, clean up your requirements spec. I'll probably have a minimum threshold for requirements for your project, but yeah, shouldn't be too bad. So other than that, I will see you all Wednesday and we'll wrap up these slides and then we'll next week move on to more exciting verification types of activities. Anyway, I hope you all have a wonderful Monday. And I think it's supposed to be start getting cold here, so enjoy the actual Michigan weather here. But you all have a wonderful day. I'll see you next time. Bye, everybody.